A very good evening to everyone. It's a great pleasure for me to invite Professor Roland Wester here. So he is a German working in University of Innsbruck as a professor in the division of molecular. He did his PhD in the University of Heidelberg in 1999, followed by 2 years of postdoc in the University of California in Berkeley. I hope it is all correct. And then so this he did his PhD in Coulomb explosion imaging of molecules, followed by femtosecond spectroscopy in University of California. Then 10 years, around 7 years, he worked in the University of Freiburg. And then he joined Innsbruck as a full professor. It was from 2010 onwards. And I don't want to say more about his interest. I think you will hear from the talk what interest he has and what he's going to talk about. I'm really happy to see that so many students are here, even though there are exams going on. Thank you for everyone for joining. And so in the morning we went to some places and we had seen some waterfall. Said there is some waterfall in his talk, and he will say what is the relation with this talk. He is talking about spectroscopy and reactions of molecular negative ion or even probably atomic negative ions. So what has it to do with the waterfalls? I guess it has something to do with negative ions. Let's see. Okay. So his area of work actually is very interdisciplinary. Astrophysics of interstellar medium and the biomolecular and the fundamental physics, chemistry. So there is a lot. So you see what kind of work Roland is doing, and let us hear from him. So thank you, Roland, for coming all the way here and visiting our institute. For you, yeah, now the chair is yours.
Thank you. Thank you very much, Sunil, for this very introduction and for the invitation to come here. I was meaning to come to visit Tirupati for many years, and I'm very happy finally this worked out. And I had some very nice days here already, science, seeing many labs and also enjoying the outdoors a bit. Yeah. So I'm trying to think where I stand. Probably I best stand somewhere up here. Yeah. I'm going to talk about negative ions, and I will give you a broad introduction on why they are interesting. This will not be exclusive, but there will be several interests related to the work that we're doing. And then I will talk about spectroscopy and reaction. This is, of course, a very broad field, and I could talk about many projects we've done over the years. I will highlight a few, as you see. One from the start of the work in Innsbruck, and then a few very recent ones. One actually was submitted only last week. So Innsbruck, for those who are, is a city really in the middle of the Alps. This is the city of Innsbruck here at the very west of it, west direction. I'll have a map on the next slide, is where the technical campus of the University of Innsbruck is located. And you can see very characteristic are these very high mountains. So altitude gain of almost 2,000 meters from the valley bottom, top peaks here, and that within a very few kilometers horizontally. So it's really a very, if you want, the solid angle of the sky is actually as small as it can possibly get in a large in Europe. So Innsbruck is here. You can see in the middle of the Alps, really very west end of the state of Austria. Germany is to the south. And Innsbruck is a fairly old university, not among the oldest in Europe, reasonably old, from 1669, about 27,000 students and about 5,000 members working in all fields of sciences and humanities and also some engineering fields. Yeah, that's sort of, and the capital of Austria is over here, about 400 kilometers further to the east. Innsbruck, just a few pictures also, as I said, is between high mountains. Of course, there's lots of snow in the winter. You can see here We got the first picture of snow 2 days ago on this winter. And there's also some famous architecture from the imperial times. This was a big city, was ruled by the Habsburg emperors. And for example, this famous golden roof was devoted and donated to one of the emperors 500 years ago. And you can see the river valley that is sort of crossed here. So we are there for about 15 years now, and we're doing various things related to ionic systems. Much has to do with negative ions, to do with positive ions. And there's various topics, reaction dynamics, so the chemistry or the underlying, if you want, molecular physics underlying a chemical reaction is one of these topics. But also then more controlled collisions, in particular, being able to prepare quantum states is another such topics. And then there's larger systems such as water clusters of species and how individual water molecules affect reactivity. Biomolecular ions is an important topic. Actually has become even more through a recent collaboration with 2 or 3 years. We had a project together studying biomolecular ions and their photochemistry, photophysics. And I will not say much about that. That sort of would be another talk. But that's something we do. And we also work on interstellar ions. So the chemistry, the physics of particles in the cold areas of our galaxy where aggregates and leads to the formation of stars in an evolution period of maybe some billion years or so. So these are kind of the overall topics within the group. And now I would like to come back and look into negative ions. Why are negatively charged species actually interesting in such environments? Of course, reaction dynamics, also interstellar physics, all these topics are relevant for neutral species, also for positive ions. Well, there's various reasons. In liquid chemistry, if you think about salts, put it into liquid and how chemistry, you have also always a negative and a positive ion. So, just think about simple putting that into water, it solvates into sodium cation and the chlorine anion. And so if the chemical reactions, there's always related to negative ion, the negative ion charges, solvation effects, all sorts of things. The ionosphere, I have a slide on that, contains a section of negative ions that also determine the properties. And of course, the ionosphere is also of very this is important because if you want to do radio communication over long distances, in particular when you don't want to go via a satellite, then the ionosphere is reflecting radio waves. You can actually do communication over essentially the entire globe if you do it right. Well, very nice experiments on plasma physics earlier today. And in plasma, there's not only cations playing a role. And if you want to understand really the details, you may also want to look into this. And then the interstellar medium I already mentioned, and I also will show how negative ions appeared on that. And finally, also in combustion, there are negative ions, not only positive and not only alongside. And so just to give a bit more detail on the atmosphere, because it's a gas phase environment where ions play a role, I have here on the left side the temperature profile of the Earth as a function of height. So here you see that's us at 0, and then 50 kilometers, 100 kilometers, that's already high above the troposphere, which is down here. So most of that down here is the stratosphere. Then we have the charges really go up about 100 kilometers above where the electron density goes up very high, and sorry, the temperature of the electron goes up very high. Also, the density will go up, and also the gas density goes up here and reaches, in fact, thousands of Kelvin, which where particles can also be almost thermally ionized to a significant fraction. And when you look at the abundance of species, then you find that as a function of the height, and this starts at 50 kilometers on the right of the graph. Actually, I'm not sure you see this online, right? I don't think you see the pointer online, but maybe you have a. So I'll try to talk about also where I'm pointing. So 50 kilometers to is the altitude here on the right side in our atmosphere, and it's maybe simpler to come from the top. From the very top, it's mostly nitrogen and oxygen. Actually, almost all the ions up here are plus ions. A lot of N plus, and then also lower amount of protons and of helium ions. That goes along with the high, in red here, a high electron density. So these are effects created by positive ions and free electrons. But then around 90 kilometers, the electron-ion plasma stops, and we have an ion-ion plasma starting. And there's lots of negative ions also up here. And most likely, sulfate ions and nitrate ions are also responsible for aerosol formation in these high-altitude regions between 60 kilometers and so on, and are therefore then later on responsible also for cloud formation. And so, and you can say the same not only for the Earth's atmosphere, but also for other planetary atmospheres. Of course, we know within our solar system, there are atmospheres that are very similar, or at least somewhat similar to the Earth. Titan, a moon around Saturn, is one example where negative ions have been found. But now we know about 6,000 exoplanets outside of our own, and many of those are already known to contain something like an atmosphere. Most likely also in those atmospheres, not only neutrals and positive ions, but also anions. And then the other big topic in the group over many years has been the presence, or about the presence, of negatively charged species in the cold environments in interstellar space. Three view graphs here, three papers on this view graph over the decades. This was 50 years ago. Alex Dalgarno and McRae, they already speculated about the formation of negatively charged ions. This was decades after the first positive. And then a few years later, there was more on the possible detection. Still, 1980, this was all speculation. 1981 came a paper by Eric Herbst, a very well-known modeler of interstellar, that created some very clear prediction for making negative ions. Still, it would take another 25 years or so until negative ions were finally discovered, and that's in part due to telescope here. This is a big radio telescope, about 100 meters in diameter is this dish. This is a huge telescope detecting radio waves from these clouds, located in West Virginia in the United States. But there are several other telescopes of size around the world, and also these days very sensitive ones with even a bit smaller dishes that can detect radio emission of molecules from space. And here's a list of papers. I will not go through the details. Many astronomical environments where such, but you can see here is a list of negatively charged species. Very strange species, maybe the most familiar one, some of you maybe Cn minus. This is the negative ion of the HCN, or so the cyanide anion in potassium cyanide. It's highly toxic environments also. And then there are other species which contain more and more carbon atoms, as you can see here. And they all have very linear structures, which is because that's how they can be detected. And so it's out there. And the question, of course, is then, so why are they there? What do they do there? How important are they of interstellar clouds, and so on? And so for that, we have to study the laboratory properties. And essentially, that's where we come in. And there's many questions you can now ask now that we know they are around in certain environments. They do things maybe in these environments. How can we describe what they do? And essentially, you can answer such questions where when you look at molecules, and that means by interacting these molecules with light, could be radio waves, could be infrared light, could be visible, ultraviolet. And then you can test the structure, and you can check if theoretical calculations are actually able to predict structures properly. Part of that is to test the binding energy of the electron, because once the electron is gone, the negative ion is no longer negatively charged. And so this binding energy, or the electron affinity of the species, is a very important quantity. Once you know spectra, you can look for these species. In a plasma discharge, you can look for signatures, or in interstellar space, you can look for signatures. And for that, you need the spectroscopy. And then, of course, there are more things, in particular, like the ones we just recently looked at together with Sunil, large DNA fragment anions. There also the photophysics and the photochemistry is interesting. So breaking, formation of fragments, all sorts of things that happen when such an ion absorbs a photon is of interest. Of course, not only the phenomena are interesting, also the probabilities, for example, for photodetachment, which is the elementary process of taking an electron away from a molecule. And in that respect, the photostability. Think about in ions, that's where we worked on many years ago. When you have interstellar ions, that can be destroyed. Well, if there is a star nearby, well, the star may destroy or will destroy the ion. And the important question is how long for the radiation to do that. And then, of course, there are more fundamental questions like, can we learn something about the long-range electron-neutral interaction? And I will come to that at the end. Can something to the ions, like cool them? I mean, there's a big field in atomic physics, in particular, atoms or cooling positively charged ions with laser light for doing quantum operations on them. And the question is, can you do that with negative ions? Well, the simple answer is we don't know, because nobody has been able to do it so far. Mm-hmm. So this is just the study of the properties of these species alone, ideally. But then, of course, they interact in an environment like atmospheric clouds or clouds. And so you have to understand also oops, what's this? You have to also understand their collisional properties. Ideally, of course, when you think about this as a fundamental, a single atom or a single molecule and a single ion, and see how their interaction takes place. What are the products? What are the cross-sections? Can we also learn something about inelastic collisions, quantum effects? That's, of course, a very fundamental question. How important is quantum physics for all of these effects? Because it turns out that over the last century or so, most of the chemical understanding and chemical intuition has actually evolved in sort of semi-classical terms. And not very many reactions are really driven by fundamentally quantum mechanical dynamics of atoms, I should say. The electrons are always treated quantum mechanically. And so that's the field of reaction dynamics where I will not say much about. I will have an example at the end. And of course, collisions can also. And so all of this is a sort of, that's basically the research or the questions that drive the research of my group and also many groups around the world. I will really only highlight a few examples in this very, of course, will not be exclusive to this. But that's sort of why this is interesting. And coming back to walls, negative ions are also good for your health, it turns out. And here's a review article from 2 years ago, which just looked at the meta-analysis at all the art decade before that studied the effect of negative ions on by inhaling ions. This stimulates the immune system. And it's statistically hard to nail down how important the effect is. But it seems from this that it's a statistically non-zero effect. And that's why you find at least signs in places. This is a waterfall, famous one in Tyrol nearby. I'm sure it's the same at this very beautiful waterfall we visited this morning, that negative ions get created there. And if you inhale them, if you sit there and relax, it's not just good because you can relax, maybe good because you can inhale some negatively charged species. And this is actually recent, but it turns out this has already been studied more than 100 years ago. This is 1890, so 135 years ago, where it was named the Leonard effect. Philip Leonard, first famous and then later very infamous physicist in Germany, in Heidelberg actually, where both O'Neill worked for some time and I worked for some time, discovered this in his habilitation thesis. And in fact, what happens is that water that splashes to the ground produces in particular negative ions and negatively charged particles, aerosols maybe, that fly up because the ground tends to be more positively charged, and so the splash, the ground tends to be negatively charged, so it absorbs the positive charge carriers and ejects and repels some negative charges into the air. If the particles are small enough, they will not just directly fall down again. Yeah, this is sort of the habilitation thesis. Leonard also worked a lot on gas, was close to discovering the electron, was close to discovering X-rays, and then later on turned, if you want, really to the dark side because he sided with the German Nazis in the 19. Oops, touching this, and was fighting quantum relativistic, special relativity, and these things, what they call sort of Jewish physics at the time. So he really became very infamous. But this was sort of decades before. And the negative ions, of course, are still around if you go to such falls. Any negative ions, if you look at the periodic table, many species bind an electron because, of course, the first moment when you think about it, you ask, how strong is actually the binding energy of an electron to a neutral? Well, if you look at the periodic table, or you look at all the atoms here along the periodic table, you see that the binding electron affinity, which is a property defined as the property of the neutral, ranges from 0.7, which is already much, much more than room temperature thermal energy, all the way to 4 eV or so, 3.5, close to 4 eV for the halides, fluorine, chlorine, bromine, iodine. Gold has a very high electron affinity. But most species actually have a positive one, and so they do bind. And even more so when you look at molecular ions, because many molecular ions, in particular when they're electronic structure, are very stable, like OH minus radicals, CN minus, and many more, including also deprotonated glycine amino acids. So essentially, you have a nice stable molecule, and you remove a proton, you deprotonate it, you create a stable negative ion. Of doing it, and also all these carbon chain anions are here. So many species are actually very stable, even more than these halides, and so they survive for quite some while and can be studied. And so this is sort of to set the stage, you know, where negative ions are. And now I'd like to share with you some results, how we do experiments, and what kind of things we can learn. I will start with OH minus, which is really a species that has been with the group since 2008 or so, and then come to some very recent results on the C2 minus negative ion. This is sort of two spectroscopy examples, and then I will two examples of reactions. One very fundamental one, and one that is very much close to the heart of many organic chemists. Yeah. OH minus is a molecule composed of these two atoms. Of course, molecules are described by their potential energy surfaces. This is a calculation of our long-term collaborator, Murthy, and co-workers on these potentials. There are, of course, also many others in the literature, but this is shows you very nicely the ground potential curve of the negative ion here in black, and the bound potential state of the OH neutral radical here, the doublet pi. These are all the spectroscopic notations. The molecular physicists will know them. Everyone else will know them. We don't really need to know much about these for this talk. What's important to note only is nothing in between. You know, atoms have many excited electronic states. Remember the hydrogen atom with its infinite series of Rydberg states. The same is true for neutral molecules. Negative ions rarely have because once you have the electron in an excited state, it tends to go and fly off directly and produce a neutron. So there are excited states here, OH minus in the A state, but this is high above the neutral. That means this will not live long. It will, you know, kick the neutral instead with a free electron, and so that means that there's only a stable state for the OH minus. And so the neutral, of course, has also other higher excited states. And so we will now focus on this part and can learn about the negative ion when we're down here, you know, this is down here in the bottom of this valley. And of course, along this internuclear distance, and they can also rotate. For most part, we will look at cold ions where vibration is not excited. So the molecules are in the vibrational ground state, this depicted, but they can populate individual rotational levels. And you can see here quantum number J0, 1, 2, scales J with J times J plus 1, so the spacing increases. And the energy difference is about 1.8 electron volt, quite substantial. It's a visible photon that can drive a transition from here, red photon, in fact. And the question is, what's the photodetachment cross-section? So how probable is it? We devised measurement schemes for that. But what we're also interested in, can we control the population states here and look at, for example, transitions between these? And what you need to do is you need to find a scheme to probe these quantum states. And then you can start to do the coupling. So the energy spacing in between here, and this is essentially pure quantum system. So it's essentially as pure a quantum as you can think of. because there's no substructure, except if you look very carefully, there's a hyperfine spin in the proton, but this is completely decoupled. So you can really think of this as a pure rotation system with angular momentum 0, 1, and 2. And of course, this is triply, and this is 5 times the general, 2j plus 1. The energy spacing here is 37 inverse centimeters. The Coulomb unit we always like to use, which is a few, about 5 milli-electron volts from here to here, or 54 Kelvin if you multiply that by K Boltzmann. So all these energy units we often use interchangeably, which means at room temperature, all these levels will be thermally populated. But if we go to low temperature, in a minute how we do that, then we can actually control the population on these temperatures. We do that. And this is where ion trapping comes in. We use radio frequency ion traps to store and manipulate and maintain our ions so that we can them. In more detail, we use multiple radio frequency ion traps. Here's of one of these devices. It's called the 22-pole trap. It consists of 22 electrodes arranged on a cylindrical surface. Every other electrode is applied, is contacted to the same radio frequency, so that effectively this creates a confining potential in the radio direction inside. So you can see here, this is the picture. Here's a cross section, and here's a cross section in the other. And there is a radial confinement by these electrodes through the radio frequency. And this was pioneered and developed over many decades by the late Dieter Gerlich. He already learned that this is much advantageous to use such multiple traps compared to the well-known and about 20, 30 years older Paul trap, because the effective potential that the ions see is very flat throughout most of the trap, and then has this very sharp onset. That leads to, if you want, this sort of box-like confinement. So the ions can drift freely inside this trapping in volume until they hit the wall, turn around, and then they can drift fairly freely again. So simulate environments like interstellar space or atmospheric environments, because that's also where we don't want electric fields to disrupt the ions. The other nice thing is you can put this whole trap on a cryostat and cool it down. This way we can reach 4 Kelvin or so, standard closed cycle cryostats. The temperature all the way to room temperature, and of course with some tricks you can also make it warmer than that. And then we add buffer gas, because we put all these different types of negative ions. I showed you many examples already, and they will be trapped inside, but then they will still have whatever energy they have from the ion source. And in lower temperatures, we add helium gas to this trap. So you have to think that this trap is actually enclosed. There's also a lid here and 2 walls on the side. And then helium gas will do collisions with this. And you can look at this empirically, or you can also make more quantitative measurements and see how the cooling proceeds, and see that within typically milliseconds of time, the ions cool down and reach effectively the temperature of the wall. It's been a long topic. How well? Well, usually they're a few Kelvin warm, or we can bring them down to close to 4 Kelvin. We can do this with either cation or anion species. And we can also look, and that's another aspect, of course, of these traps, we can also put neutral reactant molecules that maybe react with these species, and then work with those. So that's sort of the tool, and we operate in my group now three and a half, I should say. One is there standing, not used. 3 ion traps for various topics of this type. And and so essentially the technique works as such. We have a source somewhere outside by the meter. We bring ions from this ion source into this device, use also these electrodes at the end as exit end caps and entrance end caps. They get a DC voltage of about 1 volt or so. That creates the axial confinement. And then the ions get, stuck in here. And it means as long as, not infinite, but as long as we want, which can be 10,000 seconds. So typically we get tired before, so we try to do experiments on the seconds time scale, but we've seen lifetimes of 20,000 seconds or more, which is like 10 hours and then we can put gas, and we can also put, of course, laser light. here, and in the new device we also have openings here, so we can put laser light and do photophysics of these charged particles. And then we extract them again after some chosen time, send the ions to a mass spectrometer. We use molecules, most of them or almost all of them will never ever. So we really have to use this technique via mass spectrometry, and then see how much of our initial ion mass is still there, and how many maybe new masses have been formed. And in the simplest case, the decay of the parent ion of time is given by this pseudo first order kinetics. That means that the parent ion decays exponentially from an initial composition, and the decay rate, K prime, is given by the ion molecule collision rate, or maybe also the photon interaction rate, and the neutral density here, which can be either the photon flux or the neutral particle density of some reactant. And so what this means is we look at how many ions are left as a function of this on a log scale. The slope will give us this, and then if we know how many photons went in, or when we know how many neutrals were there, we know the cross sections for this process. In case it's a bit more tricky, but essentially that's how it works. And so this is now what we can do for OH minus, and we did this already quite a few years ago. This is of Rico Otto, and that was by trapping OH minus ions in the. I will skip over some of the experimental technical details, but we needed then, of course, a tuned laser here, which was a diode laser, and then scanned at near 680 nanometers, and scanned this laser across the threshold for reaching the neutral. And the result is shown here, where as a function of the photon energy in wave numbers here, from 14,600 to 14,700. In fact, we see over 6 orders of magnitude the decay of the particle. So there's basically no decay when the photon energy is too small. The photons still are the ions don't really care. But then there are some very strong steps going up orders of magnitude here, and again here, and again here. And these steps aim at different temperatures. You see here in blue, 20 Kelvin trap temperature, and in Kelvin temperature. And however, the step heights, so the plateau heights, differ. And so how can we understand this? Well, first of all, and this is something we could also look at, the electron affinity, which is the binding energy of an electron to OH minus, ground state to the ground state of OH, is this number here. So this point here at 14,740, where the last right, that's the electron affinity of the species. So this is where the ground state loses its electron. The cross section is the highest. So all the anions can now lose their electron. When photon energy is a bit smaller than that, the ground states will not be able to lose the electron, but the J equals 1 states. And at a bit lower energies, only the J equals 2 and higher will lose the electron. That means that the plateau height here will give us how many ions are around. And we can actually see this is how sort of these thresholds. This is where the J equals 2 state starts to detach. This is where J equals 1 starts to detach. And this is where J equals 0 opens. And the plateau heights, they yield the rotational populations. And by also including the matrix elements for the transitions, we can figure out the population and got that this is a rotational temperature of about 57 plus minus 6 Kelvin, and this is 32 plus minus 2 Kelvin. So I showed you it's a little bit warmer than the trap temperature, but it very nicely follows the buffer gas temperature, which is the trap temperature. And so we can really now see, we prepare negative ions, and we can cool them, and we can diagnose how cold they are. We can measure how much the population is in these different negative ions. And this is very nice. Since then, this has been, in particular for OH, applied in many environments where negative ions are studied. You may have heard of the cryogenic storage. There are a couple, mostly in Europe and in Japan, where negative ions are circulating at significant speeds in storage rings, where they also use this now for diagnosing. And we also use this for other purposes, because now that we have temperature diagnostics, we can have excitation. So we actually did a terahertz, we did a terahertz excitation by driving rotational excitations here and used this to probe. So did a 2-photon experiment. We also looked at and measured actually the rates at which these states are populated or depopulated. So there's various things you can do with this and other molecules. I will not say more about this because time is running. I don't. Yeah. Yes. So the trap temperature is measured because we have this trap, which is about 5 by 5 by 5 centimeters. We have several sensors for the copper temperature, and this is what we define as the trap temperature. We tested and have also very, very sound reasons to know that the helium has this temperature when it is inside this box. It collides with the wall very, very frequently. So the trap temperature is helium buffer gas temperature. And this we read with using silicon dioxide from this cryogenic apparatus. So we know that temperature. And the rotational temperature is determined by measuring from this level here and this level here. What's the difference in these populations compared to these populations here, compared to the ground state population? So essentially, plateau heights, we get how much is the population in 0, 1, and 2 for regimes, and the population will then tell us what rotational temperature, given an e to the minus e rotation over kt for the rotational levels. So when we do Boltzmann statistics over these states, and in fact we only included the first 3 here because below or above j equals 2 there is very, very little population. So then that's basically from these data. Actually, this blue fit and this red fit give these rotational temperatures, and you can see they are close. They're not exactly the same because in the ion trap, the ions jiggle a little bit, and that leads to a little bit of heating, and this can be simulated and is pretty well understood by now. That leads to this slight increase, but overall, this is what we get. Yeah, thank you for the question. There are more questions, please interrupt.
What is the mistake of cooling down the temperature during the ion trap in multiple RF ion trap?
So why we cool it down? So essentially, we would like to low temperatures for 2 reasons. One, because in certain environments, like in interstellar clouds, the temperature is typically 10 to 50 Kelvin or so. So we'd like to study at the temperatures of the interstellar. And the second reason is in order to control the quantum states. So the colder we get, the fewer quantum states are thermally populated. As you can see here, there is very little population in j equals 2. So essentially, we have a 2 quantum system, 2-state. When we go to 4 Kelvin, more than 95% of all the ions will be in the ground state only. So we have a pure system. And so cooling is really a nice way to purify the spectrum of the quantum states. Yeah?
Like 2 rods we need in trap. How do we optimize this now? Is there any method or is it a random?
Yeah. The long answer will probably take too long. Essentially, 22 was an empirical geometry using 1 millimeter rods over a 1 centimeter enclosed volume. An optimal radius for a certain volume. It turns out, and that way, people use these 22-pole traps over many decades, since 1990 or so, up until also used this until recently. Now we have a new trap which is made from wires, which violates this a little. Uses only 16, works similarly well. So let's put it this way: super critical, but between 8 and 16, we still see a significant change. From 16 to 22, it seems to be less of a change, and larger is probably also not necessary. And of course, there is a problem. The larger you make it, the more complicated it is to machine. No? Yes? Yeah, that's a perfect question, and it's to the next part of my talk. Yeah? So you'll see. I'll discuss that. In between. Yes.
So, the percentage of the rotation temperature is much higher compared to that 50 Kelvin. So is there any what is
You mean here?
and 32, whereas the other was 50 and
Yeah. It turns out that these radio frequencies become more and more important the lower the temperature is. And so there are some that we don't fully understand yet. This is maybe a few Kelvin warmer than we would expect, 25-ish. So like this difference we would expect here as well. So the difference stays constant. Whether it's actually it's probably because there's some imperfections in this trap design. This is something we really would like to with the new trap with OH minus. We have new data on C2 minus where the agreement is much better. So we think this has something to do with this particular trap, which we actually decommissioned, and the new trap shows also better. Before I come to this very new results, I of course have to share at least one of the stories. Sunil and I worked together quite a few years back. Right? You can see us here, both a bit younger, yeah, in a photograph taken, I think 2013 or 14, when we worked together in Innsbruck using a trap here, which was recently developed to measure absolute cross sections. I will not tell you the full story, just to say interstellar ions are interesting, and we wanted to know the cross sections for this because astronomers and astrochemists had no idea numbers to use, so they basically picked a number and said, well, this we use because we don't know it. We could measure these cross sections here in the 10 to minus 17 cubic centimeter range, and found that they're also quite large, and we're then also going more deeply with colleagues Fast and Prague and Stockholm into the role in interstellar chemistry. But this is something negative ions have been binding us already for quite some time. Yeah? But I could say more about these species, but I'd rather spend some time on C2 minus. It's a very interesting negative ion, very special, and I would like to discuss bound, and bound-free spectroscopy to come to the potential laser cooling aspects of this. So C2 minus, a diatomic molecule, again, nice and reasonably simple to capture, described again by potential curves as a function of the internuclear distance. But in this case, there is the X ground state here, two excited states of C2 minus before we get to the first potential of the neutral in blue up here. Yeah? So that means C2 minus, unlike many, at least of the small, has excited states, electronically excited states below the detachment threshold. And that means put a photon in and get a photon out possibly on a very high rep rate compared to all the other species that are, in particular the OH minus I mentioned before. Still, you do not destroy it by detachment. And that's why it has been proposed as a candidate for laser cooling. There are several other negative ions that are also candidates. The B set here decays in 75 nanoseconds. Still, it's technically challenging, and I'll show you throughout the next slides. And find it in my group very interesting, and we're working toward it. But if it works, we'll be able to tell you only in a few years, or hopefully in a few years, maybe in many years' time. C2 is also a bit funny because these are two identical bosons with no nuclear spin, carbon. And that means that there is very interesting spin rotation statistics. In the ground state, odd quanta of rotations are strictly forbidden. So this molecule cannot rotate like OH minus in any rotation number. It can only rotate in even rotational quantum numbers. In some excited states, it's just the opposite. And the electron affinity is high, 3.4 eV, so that's a near UV photon, and that means it's reasonably stable for many experiments. And so we wanted to look into this system and do the boundary on this X to B state with very high precision using CW laser spectroscopy. And for this, we of course need a scheme because, as you can imagine, we put ions in the trap, which is about maybe 500 ions, maybe 5,000 ions. That's by far a shadow on a beam, right? So you cannot do spectroscopy like you would do it here in the room, so with maybe some trace gases or so. Also, that would be hard because it doesn't absorb so well. But here you really need to do some tricks. And so what we do is we think about putting a photon to drive this up here. And then the B state will decay, but it will decay to various states. The Frank-Compton factors, so-called Frank-Compton factors for these different transitions are about 70% to go back to the ground state, but with about 30% it goes to higher excited vibrational levels, which are then metastable. And so since stable, there's no way they can easily decay. There's no photo emission because the molecule is symmetrical radiation. It means we can take another laser, which has an energy that is just, has an energy just enough to detach V equals 1, bring it to the neutral, but not V equals 0. That's the same trick as what we used for OH minus before for the rotations, we now use for the vibrations. So the energy is not enough to photodetach. It's below the electron affinity, if you want. It's this energy here. Yeah, this was 365. But it's photon enough to detach V equals 1. And so that means if we see any detachment, it means the must have done something and populated V equals 1. Of course, this is just the vibrations. There's, of course, some nasty molecular physics underlying it. Every vibrational state has rotation states, and they are J equals 0 and 2 and 4. But then they also have the electrons coupling to the rotation. So they actually have J equals 1/2, 3/2, 5/2, 7/2, 9/2. These doublets very close together. And then they couple in the B state to these doublets here. So that means we don't have a line here. We actually have several lines. I think in total, well, we'll see. I think there's 8 lines I'm going to show you. So that's just sort of the substructure. This is the scheme. So we tune this green laser, have this other laser in the trap, and watch what happens. And the signal is basically the destruction of the ions. And this was done on these transitions here, which are also referred to as the laser cooling transitions, because these are the ones we would need for doing laser cooling. And we could measure them with about 20 meters absolute accuracy, which is a significant improvement by more than an order of magnitude compared to previous measurements. There's now enough information to know where we would have to put a laser for cooling. And you can see the data here. So there is no destruction out here, and there is the increased destruction of the ions when we tune the laser, the resonance. And you can see this is an interesting shape, which can be fit by 2 Gaussians with slightly different positions, which are actually split by the spin rotation splitting. And that's exactly this splitting here between the blue J1/2 and J3/2 states. And then we go to this R2, and never mind, this is the R0 transition going from n equals 0 to n equals 1. This is the so-called R2 transition going from n equals 2 to n equals 3, which has 3 lines. There's also the P2 transition, which has several lines underneath. And so from this, we could then sort of peak positions of these lines. We could get the spin rotation splitting. We could also get the width, just the rotation, the temperature, because the width here is dominated by the Doppler width of motion, because these are freely moving particles. And so they have a Doppler broadening. And that's also why all these lines have the same broadening. And from the population, we also get temperature out. And this is just to give you some numbers. This is the current precision where we went all the way, to below the milliwave number range, so essentially the megahertz range. And this, compared to the previous measurements, is a significant improvement in accuracy, and also gives us much better numbers. And we could get temperatures out. I don't show you the numbers. The temperatures actually now agree very well with the predictions from the ion trap dynamic simulations and the buffer gas temperatures that we put in here. So yeah, this is sort of the spectroscopy, and actually in working on the spectroscopy from excited states, because this is not easy to do laser cooling, just shining in this light. We can of course try this, and we did, and I'll show you. For laser cooling, you want to cycle these photons. Typically, want to cycle maybe 10 or 100,000, several thousand at the minimum. But if 70% only fall back to the ground state, and some of them even to the wrong rotational state, you can only cycle a few photons, and then maybe 3, and then the system is in the metastable state, and that stops the whole cycling. So you cannot do laser cooling. What you need to do is what, of course, atomic physicists know for, I don't know, is you have to do repumping. You take another laser beam and apply it on a different transition from here going up to bring it back into the cycle. The only problem is, if you do the math, well, we don't know the exact number. We assume between 12 and 18 lasers are needed at least to do all the repumping, because we have so many rotational and vibrational states here. So that's why it's difficult. It's a problem. but it needs a lot of engineering to really bring all these repumping lights in, and then to close all the possible decay channels where this thing can decay to. But what was possible is to actually still see some. So we do this excitation, and now we look with a high sensitive camera integrated over. We look at the ions from the side and observed actually a fluorescence pattern. This is the fluorescence image of the trapped C2- ions in this trap. This is now a 16-pole wire trap, not the 22-pole I mentioned earlier. And we changed for this because it's so nicely transparent and brings us the light out from here. And what is roughly 2,000 ions that emit roughly 40 photons per ion to 4 pi. We have a collection angle. So this is very, very few photons that we could collect here. See it, and we could see it because we could close the cycle by collisions. So we could use buffer gas once again to bring the vibrational excitation down to the ground state. And that gave about 40 photons per second, plus the temperature by the collisions. So this is by no means cooling, but at least cycling, and we can now build on this and improve it by adding more lasers and see if we can bring the light images up and see where this takes us. So stay tuned. Give us a few. This is something we're working on. At the same time, we also did another precision experiment looking at the binding energy. I mentioned before the electron affinity. Binding energy of the electron is a very important quantity. And for this, we now take a laser and excite directly. So now the frequency is enough to go from the ground state to the ground state of C2. For this, we take the 375 nanometers here in this case and measure the binding energy of the electron. Now, I'd like to say one word about the interaction now. When we remove, the question is, what is the wave function of the electron in the outgoing channel? This can have momentum in certain cases. So it doesn't have to be a spherical wave. It can be like a P wave or a D wave going out. And it's determined in parts by the symmetry of the system. And Eugene Wigner, already many years ago, 1948, published a seminal paper about the theory of the threshold laws for, among other things, photodetachment. And he already showed that the cross-section for photodetachment scales as the excess energy epsilon to the power of 1/2 plus the angular momentum of the quantum number outgoing electron. In OH-, this L was 0. This is the nice case, strong onset, because this is e to the 1/2, which is a square root. And I showed you the square root behavior. Here, it turns out that for the ground state, from the sigma state, L equals 0 of the electron is symmetry forbidden. It's basically the selection rule for the process that there is an L in the upper state. And that's what we also measured. So we tuned the photon energy now over a wide range over this, and we can see this, the expected threshold here in this range, and you can see a very gradual increase. And this gradual increase in P-wave threshold scaled as epsilon to the 3/2. And then a little higher up, a couple hundred, so quite a bit on the spectroscopic scale, 600 about. There's a new electronic state of the C2 neutral appearing, and this one is a pi state. There's enough angular momentum so that the electron can stay at L equals 0. And here we have a very different threshold, the S-wave threshold in this case. And so this was actually possible to see because the cross-section is really super, super small in all this range here, because we could stay the noise of these ion traps using several experimental tricks quite a bit, and thereby measure this with very high signal-to-noise ratio. And I zoom into this now, so both into this regime and this regime, and show you this is the P-wave threshold here going up, this S-wave threshold here going up. And you can see, well, it's not quite as simple as root behavior, because there's actually several rotational states underlying here. Here it's like a perfect epsilon to the 3/2 state. It's a long story. Wait for the paper to come out, and you can read it all. We had to do a modeling of the rotational states and the different Hernan-London factors for the rotational states, but then we could get this fit here that includes the rotational temperatures for both. and we could get electron affinities out, which are essentially these lines here, yeah, and more numbers which agree perfectly well. This is the model, by taking a full model of much about this. And this gave us now an electron affinity which is better than 1 inverse centimeter. So we're, better than 10 to minus 5. No, close to 10 to minus 5. See here. Sorry, 10 to minus, close to 10 to minus 5 in accuracy, which is a really high accurate electron affinity and a strong benchmark for quantum calculations, which are nearby, but energy calculations like this to this level of accuracy. So that's the most recent result on C2 minus, and we hope that this comes out. Yeah. So I've been talking a lot about spectroscopy. I think minutes, but you have to stop me otherwise. Yeah. So I can continue. The next talk is about reactions. The next part of the talk is about two types of reactions. We use ion trapping, and the second one we use a very different experimental technique, crossbeam scattering. And probably have to skip that, but for time reasons. But just in one slide, how do we describe reactions between ions and neutrals? If you've done it before, you can doze off for a second. But important is the long-range interaction, which is given by a Cn, like typically a C4 divided by R to the 4 for an ion atom or ion polarizable molecule interaction. And then there is barrier. And in the simplest case, the centrifugal barrier tells you how the particles approach each other to do something, a chemical reaction or a close collision. And the cross-section for this is actually derived by Paul Langevin in this paper from 1905. So it's also something that's known in the ion atom collision community for a long time. It's a very simple equation, essentially just this number and the relative energy here, or the rate coefficient, which is the one I mentioned earlier in experiments, is just the polarizability divided by the reduced mass that determines this rate coefficient here. And this is often pretty large compared to neutral scattering, which is why ion atom scattering are also quite important in plasma environments, even though ion abundances may be low compared to neutral abundance. So this is how we describe cross-sections, and the question is this right? Well, in a simple system, A, C, we have this attractive long-range interaction. When you go out to products, you all long-range attractive interaction. There's some potential value in between, like a more complicated potential energy surface case that connects these two. We usually describe that by some reaction coordinate. How probable is it to, once you overcome the centrifugal barrier, to go out here? Well, simple assumption is 100%. If that's the case, we call this a barrierless reaction. Capture cross-section is correct, this Langevin equation. An example for that is one of the most probable reactions in our entire universe. Hydrogen molecules react to H3 plus H. This is followed by such a potential by this law. Well, but now come negative ions. Of course, this ions. And for negative ions, very often there is a repulsion of the electron orbitals when this whole together, and that very often leads to substantial barriers here, which are bottled. Even if they're submerged, they can suppress the reactivity from here to here. And that can have a strong temperature dependence also, and lead to factors of 10, 100 or more of reduction of the cross-section. And one example where this is very strong is this reaction, D minus plus H2. Negative ion reaction we think of, and maybe you find a simpler one. I don't think so. But if you find one, then please tell me. So this reaction is very symmetric, except for the D minus and H minus, H2 and HD. And that's why the Born-Hauptmann potential here doesn't account for the isotope effects. But never mind, there is a slight exoagicity. It's lower in energy here. That's why this reaction goes. But there is a barrier of about half an eV, so high, so that at low temperatures, this reaction probably will not happen. We estimated that the rate coefficient should be something like 10 to the minus 19 using a simple one-dimensional estimation, which would be 9 or 10 orders of magnitude below this rate I just introduced. So the simple theory would over-predict this reaction by 10. So we set out to do the experiment. We put D minus into this trap. We put H2 H minus. Sounds simple, is technically, conceptually very simple. Tried it several times over many, many years. 2017, we published an upper limit, which is here. 10 to minus 18 is above the reaction rate, is all we could say at the time. Range 20, 30 Kelvin. That provoked a collaborator from Florida to calculate this reaction using quantum scattering calculations. And they came up with these theoretical results here, which say, yes, the actual rate must be, more than a factor of 10 below. And of course, as an experimentalist, you say, okay, you say either I cannot do this, or you say, okay, I can, maybe I can improve the experiment. And so this so-called simple experimental procedure was improved. Instead of just trapping, we trap longer. We went to thousands of seconds, which was including some improvements. We use much more H2, in excess of 10 to the 15 particles, which problems. I will not say much about it. You can ask me later. And we also had to measure with much sensitivity, improve all the electronics. And this is what we got. So this is the ion number as a function of extracted from the trap. We put lots of D minus in. We see lots and lots of D minus. But we also see H minus product formation. And this was the breakthrough, if you want, enhancing this 30 times. There is something here. And we could then study this. Depends on the density. And gloss over this, but you can see a mono-exponential decay of D minus, which is the rate coefficient. We can see the H minus formation. Then it also lives only for. We can fit all of this with the full rate equation model, which includes all these different. Then we get a number for the formation rate of H minus, which is 5 times 10 to the minus 20 cubic centimeters per second. Or, so this is where it lies on the plot. So it fits perfectly to the theory for normal hydrogen, and is by all means, for what we know, so the lowest ion molecule reaction ever measured in the gas. By 4 orders of magnitude is what we think. 1 in 10 to the 11 collisions only tunnel through. And I should say, this is a tunneling effect that is included in the calculation. Don't include tunneling. This is the theory, and it cannot explain this rate by all means. So this full deep tunneling reaction that leads to these products. And so this is sort of a very fundamental result that, of course, was very interesting to see. And I could stop here, or I have a few minutes to talk about another effect. You let me know. 2 minutes. Yeah, so I just give you the flavor of the other experiment, and you can read more about it in the literature. We do also cross-beam reactive scattering experiments. This is sort of more the physical chemistry group, where we put also larger molecules, and we then collide them with well-defined momentum vector. Having a trap where everything is dwelling for some time, we have a single collision. Takes a microsecond or so to observe, and then something happens. We see maybe a product, and we see maybe a product ion, measure its momentum vector, and then we can measure if the momentum is slower than what we can get also the internal excitation of the molecular products, angular dependencies, and all sorts of informations like this. And we did this, for example, for this F-iodine reaction, where there's many, this is sort of the view here. More interesting is how these reactions occur. If the negative ion comes in, it hits this molecule, it can substitute another, in this case, iodine atom, and that leaves, and we can then measure the I minus. This is a very important substitution reaction in physical organic chemistry. There are different mechanisms that have been defined by theory. As you can see here, this one looks, and there's also one where this thing actually lives quite for a long time and sticks together until it decays. And these are the things we're looking at using maps like this. So this is now the velocity map of the I minus product flying either forward or backward or sideways. And we can do this for deuterated species and for hydrogenated species. Comparison that we did in a paper that came out earlier this year, where we looked at the different contributions to the cross-section here, backscattered, side-scattered, and so on, and found that there's a strong isotope effect, which we could not explain, and also theory could not explain. Look at the ratio of forward-scattered, for example, hydrogenated to deuterated. There's a big difference, and for the backscattered in particular. And this is something that theory could not capture. So here you can see the forward scattered in blue, not in the theory, for all these energies here. And this is something, if the full theory, which is a theory, cannot capture it, what's missing, yeah, and this is true for the hydrogen case. So the deuterium case agrees very, very well. Hydrogen shows a quantum effect that this classical theory could not capture. We don't know yet the full origin. Full quantum calculations for a system as large or as small as this are impossible at this point. But we know it must be a quantum effect by basically removing all the classes in the equation. And so this is one example of things we do. There's lots of other examples we do. I'll stop here. Before I come to the summary, let me say thank you very much to the whole team. Many, of course, have worked on all these projects over the years. And thank you very much, Sunil, and for all the great discussions and all the nice projects we do together. And with this, I'm happy to take further questions. Thank you very much.
Yeah, thank you very much, Roland. There was one more. Yeah, it's here. I can request you. Yeah, please. Yes. Okay, I would like to our associate chair to give this memento to
Oh, wow. Thank you very much.
Thank you.
Thank
Thank
you.
you.